Welcome back to the Deep Dive. Today, we are strapping ourselves into the world of high-stakes chemical engineering. We're taking a really deep dive into the source material that defines how the industry keeps itself, and all of us, safe.
It's a huge topic.
It is, because when most people think of chemical production, their minds often jump immediately to catastrophe. Incidents like Seveso or Bhopal.
Right, and that negative public perception, it's fueled by those catastrophic headlines, and it creates this deep inherent distrust.
That really does.
And it's true. The public perceives the chemical industry as uniquely dangerous, often, overlooking the immense societal benefits it provides. Whether we're talking about cutting-edge pharmaceuticals, essential new materials, crop protection agents, you name it.
So our mission today is to move beyond that emotional sort of a priori perception of risk.
Exactly. We want to dive into the engineering rigor that systematically manages it. And we're going to focus entirely on thermal process safety. That's the discipline of preventing uncontrolled, heat-driven events using a really comprehensive framework that moves from identifying the hazard all the way to designing a reactor that simply cannot explode.
Okay, let's unpack this immediately because there are two distinct fields of safety here that we need to define. We have to distinguish between product safety and process safety.
And this distinction is absolutely essential for understanding the scope of our deep dive today.
So what's the difference?
Well, product safety deals with the risks that are linked with the use of the chemical product once it leaves the factory. So things like inherent toxicity, environmental effects during disposal, or, say, the fire risk associated with storage and end use.
Okay, so that's the safety data sheet that comes with the material.
That's it. Our focus, process safety, is fundamentally different. It's concerned entirely with the risks linked to the manufacturing process itself. The highly controlled, often extreme world of chemical reactivity, heat management, and equipment integrity during the moment of production. This is the domain where thermal runaway lives.
And this is where the numbers really start to challenge that pervasive public perception. Our sources provide statistical metrics that reveal that while the consequences of failure are incredibly high, the likelihood is highly controlled compared to many other activities we just readily accept. If you look at the Swiss National Accident Insurance statistics, for example, for work accidents per 1,000 insured people, you find construction at a staggering 155.
Wow, that's high.
And agriculture is at 138. The chemical industry, with all its inherent danger, is way lower at 31.
It speaks volumes about the systematic safety measures in place. And the comparison becomes even more striking when we quantify the risk of fatality using the fatal accident rate, or FAR.
Right, the FAR. And this is a global standard, isn't it?
It is. It measures the number of fatalities per 100 million hours of exposure. It gives us a common yardstick.
And I found the contrast here really compelling. Let's look at the industrial FIRs first. Coal mining, historically a high risk, is at 7.3.
Okay.
The chemical industry is at 1.2. And vehicle manufacturing, a highly mechanized industry, is even lower at 0.6. These are, manageable industrial risks.
But now compare those figures to non-industrial activities where the public willingly accepts risk without a second thought.
Yeah, this is the really surprising part. Motorbike riding has a HAZOP of 660.
660, that's a huge number.
And alpinism, mountain climbing, that's a staggering 4,000.
Wow. It doesn't mean chemical risk is trivial, not at all. But it highlights that the industrial risks we perceive as catastrophic are, by necessity and regulation, extremely well managed compared to many personal choices. The engineering framework actually works.
Right. And that's systematic management, the foundation of this entire deep dive. It boils down to one simple, fundamental equation we have to keep centered. Risk equals severity multiplied by probability.
That's our mantra today.
It is. Our mission is to systematically explore how engineers transition from that simple equation to a finished, safe process, from identifying the hazard and quantifying the energy potential, right through to designing a safe, stable reactor using what's called the criticality concept.
Let's get into it.
So if risk equals severity times probability, we need a methodical, step-by-step way to quantify both of those factors before we even think about construction. The source text walks us through the sequential steps of risk analysis, starting in Chapter 1.2. Where does an engineering team even begin this process?
Well, the very first step, and it sounds obvious, but it's frequently overlooked, is defining the scope of analysis.
The scope.
You have to meticulously delineate exactly what parts of the operation are included in the assessment. And this goes beyond just the main reactor vessel. It means characterizing every single chemical, every unit operation, all the utilities, steam, cooling water, backup systems, the skills and training of the personnel, and every single regulatory requirement.
So you're saying if you're assessing a reaction, the raw material delivery from a tank farm way over on the other side of the pool.
It has to be included. It's connecting lines, the transfer pumps, they must be explicitly included in that scope. If you don't define the boundaries, hazards inevitably slip through the cracks.
And speaking of things slipping through, when incidents do happen, the cause isn't always just a mechanical failure. Our sources note that technical failures are often preceded or made worse by human factors.
Oh, absolutely. Technical failures are manageable, but human error is the constant variable. The causes of incidents frequently tie back to a lack of knowledge, maybe not having the necessary thermal decomposition data for an intermediate product. Or, and this is a critical one, non-identified deviations from the normal procedure. Someone bypasses a sensor or speeds up a feed rate to meet a deadline. Then there's just wrong risk assessment, or perhaps most frustratingly, neglecting safety measures in the push for production efficiency.
So the systematic analysis has to identify these potential human-system interfaces just as much as it checks the thickness of the pipes.
Precisely.
This moves us into the core of the systematic approach, the hazard identification techniques. We move past the intuitive methods, which are basically just brainstorming, into the quantitative, structure-driven methods, inductive and deductive.
Right. And starting with the inductive methods, these move from a component failure or an initial event, and then they trace the ensuing effects downstream. The two major tools are FMEA, that's failure mode and effect analysis, and ETA, or event tree analysis.
FMEA sounds a bit like engineering detective work.
It is painstaking, but it is so essential. FMEA is component-based. You look at every physical component, a pump, a valve, a temperature sensor, a relief disc, and you systematically define every possible failure mode.
Like failure to open, failure to close.
Exactly. Failure to start, running dry. You then define the cause, and most importantly, the subsequent effects on the system. It helps ensure the integrity of all the individual pieces of equipment that support the process.
Okay, so if FMEA tells us how a pump fails, ETA then tells us what happens to the whole process after it fails.
Correct. ETA visually charts the flow of events from an initial incident. Think back to that collision example. Starting with the initial incident, deer on the road, you map out sequential branches based on the safety barriers and subsequent events. Did the driver see it in time? Did the brake work?
Was the passenger wearing a seatbelt?
Right. And this leads to all the possible final consequences: collision, injury, no injury. ETA is particularly useful because it's an inductive tool that helps you quantify the resulting probability by multiplying the probabilities along all those branching pathways.
Now contrast that with the deductive method, which is fault tree analysis, or FTA. This kind of flips the script completely.
It does. This is where you move from cause to effect to cause. Instead of starting with a component failure, you start with the worst possible outcome, the undesirable pop event, let's say reactor rupture.
And then you work backwards from there.
You work backward, building a hierarchy of all the underlying causes and failures that must combine to trigger that event.
And this framework is totally reliant on logical gates. This is where engineers really introduce redundancy and layers of protection, isn't it?
Absolutely. The OR gate means that any one of the events underneath can cause the top event. If the pump fails or the valve sticks, the reactor overflows. Conversely, the AND gate is really the foundation of modern safety design.
Why is that?
An ND gate means all events below it must occur simultaneously for the top event to happen. When you require simultaneous failures, say the main cooling loop fails, and the emergency power for the backup cooling fails, you are multiplying those conditional probabilities.
Which results in a much, much smaller number.
Exactly. A significantly exponentially smaller overall probability of catastrophe. FTA helps engineers visualize exactly what independent layers of protection are required to convert an undesirable or R relationship into a significantly safer A&D relationship.
But the real cornerstone technique for identifying deviations in chemical processes is the HAZOP, the Hazard Inoperability Study. This is what forces the team to look past the design specs.
HAZOP is systematic rigor applied to the process flow diagram itself. It involves applying standardized guidewords to process parameters at every single node of the operation. And these guidewords force the team to imagine scenarios that fall outside the normal operating window.
It's a very structured process.
Meticulous documentation. You apply the guide word to a parameter, define the resulting deviation, hypothesize the cause, and then assess the consequence.
Let's talk about those guide words from Table 1.8. It gives you a real sense of the thoroughness required.
Sure, let's take the parameter flow, for example. The guide word no not means a total negation of the design intention, so you get no flow or no agitation.
And the consequence of that could be?
Potential accumulation of reactants and localized overheating, a hotspot.
Okay.
Then you have less. That's a quantitative decrease, a flow rate that's too low, or a temperature that's too low. This might just mean slow production, but it could also lead to dangerous accumulation of unreacted feed if the cooling is still active.
And more is just the opposite.
A quantitative increase, like the temperature being too high or flow rate too high, the consequence there is potentially triggering an undesired side reaction or just overwhelming the cooling system.
What about the qualitative ones, like
As well
as well as?
That suggests a qualitative increase. So, for instance, your raw material is contaminated with an impurity. And this is crucial because that impurity might be a catalytic time bomb, accelerating decomposition at a much lower temperature than you'd ever expect.
So this systematic, almost military-like application of guide words ensures comprehensive coverage. You're moving beyond just intuition.
Exactly. You're ensuring that every possible mechanical, human, and qualitative deviation is considered before you ever break ground on construction. Once those scenarios are identified, we move to the final assessment step, the matrices.
Right, the risk matrix. How do engineers define an acceptable versus an unacceptable risk using this approach?
We combine the severity categories and the frequency probability categories into the risk matrix. Severity is ranked systematically. At the low end, you have negligible, which means no injury and short-term, low-cost production loss.
Okay.
Moving up, marginal might involve a first aid injury and production loss of a few days. Then you hit critical. That means serious injury or a major incident like a large environmental release with production interrupted for up to 6 months.
And the worst is catastrophic.
Catastrophic is defined as one or more fatalities, production interrupted for over 6 months, or the company's very survival is threatened.
And the probability categories are also very granular, right? From A to F.
They are. Category A, frequent, happens more than once every 10 years. Think of a localized power failure without a backup. Down to Category F, almost impossible, which is less than once in 100,000 years, reserved for true black swan events, like a heavy earthquake or an aircraft impact on the facility.
I noticed our sources specify a preference for a 4x6 matrix over a simpler 3x3 grid. Why is that specific size preferred?
It's all about discrimination, particularly in the most critical area. Low probability, high severity events. A simple 3x3 matrix often just lumps too many scenarios into the same category.
Forcing you to either over-design or under-design your protections.
Exactly. The 4x6 matrix, with its 6 frequency categories, allows for much finer control over the risk reduction factor required. It helps you precisely define the acceptable risk tolerance boundary, differentiating what's truly unacceptable risk from just undesirable risk.
Before we move on to the physics of heat, let's briefly touch on the non-engineering data needed for the scope definition, safety data essentials. This is about the material's inherent hazard outside of its reactivity.
Yes, this characterization is vital for containment and for emergency planning. We need toxicology data like the lethal dose, LD50, and lethal concentration, LC50. But for assessing the acute short-term impact of an accidental release on the surrounding human population, we rely heavily on the acute exposure guideline levels, or AEGLs.
Can you walk us through the practical application of those 3 AEGLs?
Sure. Let's use acetone as an example. AGL1 is the airborne concentration where the general population might experience some discomfort, maybe an odor, or non-disabling irritation. It's the limit for short-term exposure that requires no intervention.
Okay, so that's the annoyance level.
Pretty much. AGL2 is far more serious. This is the concentration where serious, irreversible, or long-lasting health effects could occur. This is the level that triggers immediate protective actions, like sheltering in place or evacuation.
And AGL3 is the worst.
AGL3 is the highest level, indicating life-threatening health effects or death. These levels are absolutely critical for designing emergency response protocols, sizing relief systems, and planning evacuation zones.
So AEGLs inform the human impact. What about the necessary environmental data?
Right. Beyond human health, our assessment has to include ecotoxicity data to assess the environmental impact from potential spills or discharges. This requires metrics like toxicity to bacteria and critical metrics for aquatic life, including algae, daphnia, and fish toxicity. These are used when designing waste treatment protocols and assessing the potential environmental severity if containment is lost.
That systematic hazard mapping really sets the stage. Now we dive into the physical reality of chemical disasters. Heat accumulation, exothermic reactions are the engine, and cooling failure is the accelerator. Chapter 2 opens with a truly terrifying case history, storage during the weekend. This is a perfect illustration of how thermal risk is so often underestimated.
This incident is a textbook example of a static system failure. An intermediate product was routinely produced and then stored at 90 degrees Celsius in a large unstirred vessel over a weekend shutdown. On Sunday night, the storage vessel exploded.
And the initial perception was just, it's storage, 90 degrees is safe.
Exactly, but the decomposition temperature was much higher, around 200 degrees Celsius, right? So how did it bridge that 110-degree gap?
That's a question.
The initial error was assuming the large storage vessel behaved isothermally, that any heat generated by slow decomposition would instantly dissipate to the surroundings. But in reality, in a large unstirred vessel, heat accumulates.
It creates a hot spot in the middle.
Precisely. Post-incident analysis revealed the product exhibited a decomposition reaction starting at 200 C, with an energy release of 800 kilojoules per kilogram. Even a small, slow decomposition generating heat over 48 hours, coupled with minimal heat loss, was enough. The accumulation of energy raised the core temperature. Once the temperature crept up, in this case, an estimated 12-degree rise was the critical tipping point, that temperature increase accelerated the decomposition exponentially.
And that led to rupture and explosion. The terrifying lesson is that for highly energetic compounds, even small, slow exothermic processes are potential time bombs if heat accumulates.
You have to calculate the potential, even if it's far above your operating temperature. And that potential is measured by the basic physics of heat management. We start with heat capacity, TCPLers.
Right. Heat capacity is the material's ability to absorb punishment, so to speak.
That's a good way to put it. It's the energy required to raise the temperature of a unit mass by 1 degree. Water is the gold standard, with a high heat capacity of 4.2. Most organic compounds, which form the bulk of specialty chemical manufacturing, are significantly lower. Acetone, for example, is 2.18.
So they heat up much faster for the same energy input, which increases the inherent thermal risk.
It does. And the heat balance in a reactor isn't just about the main reaction. There are multiple inputs to consider.
Like what?
The first is sensible heat due to feed. This is particularly critical in semi-batch reactors. If you're adding a cold feed stream to a hot reactor, that stream helps remove heat. But if cooling is suddenly interrupted, that cold feed is immediately lost as a critical heat removal mechanism, leading to a rapid temperature rise.
And you mentioned another one.
The second is stirrer heat dissipation. For viscous masses common in polymerization, the sheer energy input from the agitator blades has to be included in the total heat balance equation. That mechanical energy is converted entirely into heat.
And that can significantly drive up the temperature if cooling fails. This all culminates in the most crucial theoretical metric for thermal severity, the adiabatic temperature rise, or delta Todd. This defines the absolute worst-case scenario.
Precisely. Delta Todd is the definitive measure of severity potential. It's the maximum temperature increase the reaction mass could experience if all the heat generated by the reaction is converted entirely into heating the mass, with zero heat loss to the surroundings.
So a large delta Todd is an immediate red flag.
A huge red flag. It signals a high severity risk because if cooling fails, that entire potential will be realized and may exceed the reactor's structural limits or trigger secondary reactions.
And the mechanism of runaway is so dangerous because the temperature increase and the reaction rate feed back on each other exponentially. It's like compounding interest on destruction.
That is the core physics of thermal runaway. Under ideal adiabatic conditions, temperature rise accelerates the reaction rate exponentially, producing more heat. This heat produces more temperature, which produces even more heat.
The only thing that eventually slows it down is running out of fuel?
Running out of reactants, yes. But the temperature increase always dominates in that critical initial phase. Our sources show that for a typical exothermic reaction, you see a dramatic acceleration in the reaction rate just during the first 8-degree rise. Once that initial thermal ignition is achieved, the reaction rate just explodes.
So engineers need a way to visualize this dynamic stability and sensitivity, and that's where the Semenoff diagram comes in.
The Semenoff diagram is perhaps the most elegant graphic tool for visualizing thermal stability. It plots two curves, the heat release rate and the heat removal rate against temperature.
And the heat release rate is exponential, right? It curves upward.
Drastically.
Right.
While the heat removal rate, just Newtonian cooling, increases only linearly, it's a straight line.
And the geometry of where those two curves cross is what defines stability.
Yes. In a stable system, you want that heat removal line to be steep and always above the heat production curve. The diagram shows two possible intersections. The lower temperature one, S, is a stable equilibrium. If the temperature increases slightly, the linear cooling dominates, and the system cools back down to S.
And the other one.
The higher intersection I is the unstable equilibrium. Any temperature deviation above I means the exponential heat production instantly exceeds the linear cooling capacity, and the system runs away. The key is point C, the critical temperature, where the cooling capacity exactly matches the maximum heat production. Any deviation above that point guarantees runaway.
So stability is directly tied to cooling capability. That leads us to the sensitivity of the system to the coolant temperature.
This is where the advanced analysis gets essential. If the sensitivity of the reaction temperature to the coolant temperature approaches infinity, it means the system is sitting right on the edge of that critical point C.
A really dangerous place to be.
Extremely. Minor, unavoidable fluctuations in the cooling medium, say, the cooling water gets a bit warmer in the summer, can lead to massive, unpredictable temperature increases in the reactor. This is the parametric sensitivity region we see in the stability diagrams, and engineers must design processes to operate far, far away from it.
We've established the concept of runaway using the Semenoff framework. Now, let's apply that knowledge to the systematic risk assessment procedure, starting with the sulfonation case history. This example drives home the need to look beyond just the main reaction.
This was a disaster driven by a lack of thermal data on secondary reactions. A sulfonation was controlled between 120 and 125 degrees Celsius, managed by 2-bar steam circulating in the reactor jacket.
So the steam was for heating.
Yes, but the issue began when a procedural failure caused the temperature to creep just above 125 C. This apparently small increase triggered a highly energetic secondary decomposition reaction involving the final product.
What happened when that secondary reaction kicked in? Did the existing system help at all?
It helped initially, but not nearly enough. The 2-bar steam in the jacket was designed to heat the system, but when the temperature went above 125, the steam condensed.
So it became a heat sink.
Right, effectively providing a heat sink at 120 C. However, the heat generated by the secondary decomposition was so massive, it just far exceeded the heat removal capacity of the jacket, that the temperature continued to rise uncontrollably. This led to reactor overpressure, rupture, and heavy damage.
The crucial lesson here is that knowing the decomposition energy potential and its specific triggering temperature is non-negotiable for designing safety systems.
Absolutely. Which brings us back to quantifying severity using the metrics we introduced earlier, delta TED and the total heat release, $2.
Right. The framework provides clear boundaries for this.
It does. For a risk to be classified as catastrophic high, it must involve an adiabatic temperature rise greater than 400 Kelvin and a heat release greater than 800 kilojoules per kilogram. That's the zone of immediate rupture.
And medium critical.
That falls in the range of delta TED between 200 and 400 K and Q orders between 400 and 800. In contrast, if Q orders is less than 100 and there's no pressure buildup, the risk is generally considered low negligible.
This quantitative severity assessment then leads directly into the sophisticated heart of the assessment framework, the criticality concept. This defines risk not just by energy, but by stability over time.
Yes. The framework categorizes thermal risks into 5 criticality classes by systematically comparing 4 specific temperature metrics. Let's just restate those temperatures as they are the keys to the kingdom.
There.
You have TQT dollars, the normal process temperature, MTSR dollars, the maximum temperature of the synthesis reaction, assuming total cooling failure, the TD $24, the temperature at which the time to maximum rate under adiabatic conditions is 24 hours. That's a standard stability benchmark. And finally, MTTT dollar, the maximum technical temperature, the safe physical limit of the reactor.
So let's walk through these classes. What are classes 1 and 2?
Classes 1 and 2 are the low-risk scenarios. In Class 1, if cooling is lost, The MTSRs is less than the reactor's limit, the MTTDO, and it's also below that 24-hour stability mark, TD24. The decomposition reaction is simply not triggered.
So no special measures needed.
Right. In Class 2, the MTSR is still less than the reactor limit, but it's above TD24. This means long-term heat accumulation could eventually trigger decomposition. So you might need safety barriers like evaporative cooling, but the risk is manageable.
Now, for the critical classes where safety design is paramount, what defines Class 3?
In Class 3, the risk escalates significantly. The MTSR is now above the reactor's safe limit, the MTT-DON. If cooling fails, the heat from the synthesis reaction alone will threaten the reactor structure.
And it will trigger the secondary reaction.
Very quickly. Because the MTSR is also above TD24, so see here, high-integrity cooling and a fully specified emergency relief system are essential. You need emergency cooling or quench systems to get the temperature back down below that TD24 threshold.
That seems like a massive jump in required protection. What pushes a system into the even more dangerous zones of Class 4 and 5?
Class 4 is where we move into the domain of unavoidable high-energy events. Here, the synthesis reaction is so exothermic and rapid that the rate of heat production is faster than the maximum possible heat removal rate. The system is fundamentally uncontrollable once it ignites.
So what can you do?
The focus shifts entirely to containment or protection against that secondary decomposition. A robust, adequately sized emergency relief system is mandatory. You might even have to make intrinsic safety changes, like reducing reactant concentration to get that MTSR down.
And finally, Class 5. Runaway.
Class 5 is defined by a system that is inherently unsafe even under normal conditions. This is where the process temperature itself is above TD24 or so close to it that any minor fluctuation will lead to an unpreventable thermal explosion.
So these processes are just too dangerous to scale up.
Often, yes. They must be fundamentally re-engineered to eliminate the hazard, maybe by using continuous reactors instead of batch. If you can't re-engineer it, the risk is often deemed unacceptable.
This systematic procedure moves from a simple conservative estimate to precise measurement if the consequences are unacceptable.
It's an iterative loop. You start with a conservative estimation, assuming 100% accumulation of reactants, and calculate the worst-case delta TAD. If that calculation leads to an unacceptable risk, you must move to the precise measurement step, using calorimetry. And the key calculation throughout is estimating the time to maximum rate at the MTSR.
That tells you how much time you have to react.
Minutes, hours, or days. It's the most critical piece of information.
The power of this is highlighted in the worked example for the hydrogenation of a ketone.
A seemingly benign reaction. The desired hydrogenation had an enthalpy of 1 to 200 kilojoules per mole. Initial calculations showed a delta TAD of only 6 Kelvin for the synthesis reaction. By the severity criteria, this is negligible.
But the decomposition potential for that functional group was massive.
Exactly. Even though the main reaction was benign, the hypothetical decomposition for that class of nitro compound had an energy release equivalent to 2,500 kilojoules per mole. This decomposition potential was the latent risk, triggered only if some other failure like a faulty steam line pushed the temperature past its activation threshold.
It confirms the need to check secondary reaction potential even when the main reaction seems perfectly harmless.
Every single time.
We've established the need for high accuracy measurement if estimation shows unacceptable risk. This leads us to the instruments, calorimetry. But first, we have to confront the classic failure point in chemical engineering, the diazotization case history. This is the ultimate cautionary tale of scale-up.
This failure is a painful, repeated lesson in the industry. A blue diazo dyestuff was diazotized in the lab at 45 degrees Celsius. To boost efficiency, the chemist increased the concentration. In the lab, using a small flask immersed in a water bath, the reaction felt totally fine.
The exotherm was considered insignificant.
Right, but why? Because the heat exchange area of that small flask, relative to its small volume, was massive. It was effectively an immense heat sink. The exothermic potential was completely masked by the lab's incredible cooling capacity.
And when they scaled it up, the physics just betrayed them.
At plant scale, the specific heat exchange area, the A/V ratio, plummets by 2 or 3 orders of magnitude. The numbers in the source are stark. A lab reactor might have an AD ratio of 100. A 10 cubic meter production reactor drops to 1.35.
And the cooling capacity drops with it.
It craters. It goes from around 1,500 watts per kilogram in the lab to a mere 20 watts per kilogram in that large production reactor. You lose 98% of your ability to reject heat just because of geometry. In the diazotization case, the industrial reactor simply couldn't remove the heat density, leading to an uncontrollable temperature rise, explosion, and fatalities.
This necessitates the use of specialized tools, specifically calorimeters, which are classified by how they manage heat.
Right, the Rouquayrol classification is standard. We classify them as adiabatic, diathermic, and microcalorimeters. And crucially, they operate in different modes. Isothermal mode maintains a constant temperature, which is great for gathering reaction kinetics data.
Yeah.
Dynamic mode, like differential scanning calorimetry, or DSC, scans the sample temperature over a range. DSC is essential for quickly surveying the thermal energy potential of a substance or spotting those secondary decomposition peaks. It's the industry's fast scanner.
And then there's adiabatic mode.
This is the safety engineer's hammer. It completely eliminates heat exchange, so all the heat generated by the reaction goes directly into heating the mass. It simulates the exact conditions of a total cooling failure runaway.
But we have to talk about the unavoidable practical complication in adiabatic calorimetry, thermal inertia, or philanders. This is where the lab data can still be misleading if it's not corrected.
Thermal inertia is the correction factor for the fact that the test cell, the little metal bomb holding your sample itself, absorbs heat. If you ignore this fact, the temperature rise you observe in the lab test will be lower than what would actually occur in an industrial reactor where the mass containment ratio is different.
So first tries is the ratio of the total heat capacity of the cell and the sample, divided by the sample's heat capacity alone.
That's the math. But here's the critical consequence for the engineer. If you conduct an adiabatic test and your thermal inertia is, say, 5, it means the observed temperature rise you measured is only 1/5 of the actual potential temperature rise the pure substance would undergo.
So you're designing a safety system based on a 5-fold underestimate if you fail to correct for it.
You are. Industrial reactors typically have a phi between 1.05 and 8, which is much better than lab glassware, but that correction must be applied to ensure the scaled-up data is accurate.
For designing safety systems, like emergency venting, you need a highly specialized tool that can simulate the sheer violence of a catastrophic runaway, including all the gas generation.
And that is the role of the vent sizing package, or VSP2. It's a specialized adiabatic calorimeter, essentially a small, robust autoclave. Unlike standard calorimeters that just measure temperature rise, the VSP2 is specifically designed to measure the amount of liquid, vapor, or non-condensable gas that's discharged during an aggressively fast runaway event.
And that data is what you use to size the rupture disk.
That pressure and flow rate data is absolutely critical for calculating the precise required diameter of a rupture disk or a safety relief valve. If that vent is undersized, the reactor still ruptures violently.
If Chapter 4 showed us how to measure the heat, Chapter 5 explains where that fatal energy actually comes from, focusing on the hidden danger of secondary reactions. The storage during repair case history once again underscores how a seemingly minor procedural deviation can trigger a catastrophic thermal event.
This incident involved a semi-batch reaction using a volatile nitro compound dissolved in dimethyl sulfoxide, or DMSO, and water. The process was stopped due to a cooling failure, and the reactor contents were just left static for 5 days.
So the system was already compromised by accumulation.
It was. Then a maintenance crew mistakenly introduced 160-degree steam into the jacket. The solvent mixture boiled at 118 degrees and just evaporated away.
And the crucial failure wasn't just the heat. It was the effect of that heat on the composition of what was left behind.
Exactly. The boiling and evaporation served to dramatically concentrate the heat-producing nitro compound mixture left in the vessel. This concentration pushed the mixture past its stability limit, leading to an aggressive secondary exothermic reaction.
Probably an autocatalytic decomposition.
Likely, yes, and it resulted in a massive explosion and significant financial loss. The engineers had only analyzed the initial dilute reaction. They tragically failed to assess the energy potential of the highly concentrated accumulated intermediate.
Let's put the energy scales side by side to really understand the magnitude of this threat.
Synthesis reactions, the ones we control, have moderate exothermic energies. Neutralization, up to national 105 kilojoules per mole. Sulfonation, up to national 154. Polymerization of styrene, negative 50. These are manageable reactions.
The danger lies elsewhere.
It lies in the secondary reactions, primarily decomposition. Decomposition is fundamentally more dangerous because it releases extremely high energy and generates massive pressure due to non-condensable gases.
And the functional groups that define this high risk are common in specialty chemical manufacturing.
They are Highly volatile functional groups like peroxide, nitroazide, and triazine groups are chemical time bombs. Their decomposition energies can range up to 480 kilojoules per mole, just dwarfing the synthesis reaction energy. These are the reactions we have to avoid triggering at all costs.
And the ultimate cause of containment loss is pressure. And pressure increases exponentially during a runaway.
Right. The pressure rise has two critical and often concurrent sources. First, gas release. The formation of non-condensable gases like nitrogen or carbon dioxide during the decomposition. This pressure is calculated with the ideal gas law. And second, vapor pressure. As the temperature increases exponentially during a runaway, the vapor pressure of the liquid reaction mass also increases exponentially. That rule of thumb is a good visualization. Vapor pressure typically doubles for every 20-degree increase in temperature.
So a 100-degree temperature jump could increase the vapor pressure by a factor of 32.
It's a massive increase, and the comparison of kinetic energy potential is shocking. It gives a sense of the sheer violence involved.
It does. It drives home the difference between a controlled process and a chemical explosion.
If a synthesis reaction releases 100 kilojoules per kilogram, a secondary decomposition might release 2,000. That difference in heat can translate into a 1,000-degree adiabatic temperature rise, and the mechanical potential of that decomposition heat is staggering. It can generate kinetic energy equivalent to a velocity of 2 kilometers per second.
That's Mach 6.7.
Mach 6.7. That is far beyond the design strength of typical vessels, leading instantly to fragmentation and explosion. That is the difference between a boiling kettle and a fragmentation grenade.
And beyond the inherent chemistry, simple process deviations can introduce massive instability, especially human charging errors.
Oh, charging errors are a paramount risk because they increase the total accumulated energy potential. Add 10% too much of a key reactant, and the total heat release will be 10% higher, the MTSR will be higher, and your time margin to disaster will be shorter.
We also have to consider the impact of solvents.
Absolutely. Solvents don't just dissolve reactants, they participate in the system's energy balance and reaction kinetics. The DSC thermograms that show decomposition in different solvents really highlight this.
Right. Figure 5.6 is incredibly telling.
It is. The decomposition of a compound in heptane is rapid and violent, but using tetrachlorocarbon, the reaction is delayed and the rate is moderated. The solvent choice acts as a critical safety valve, fundamentally altering the thermal stability profile.
Which makes detailed thermal testing of every solvent system mandatory. And finally, you have the insidious risk of catalytic impurities. These are the true unknown unknowns that challenge even the most meticulous planning.
Impurities are often overlooked, but can drop the decomposition temperature dramatically. Traces of metal ions, rust, or simple salts can catalyze decomposition reactions, turning a safe process into a Class 5 runaway risk.
The source material gives some dramatic examples.
It does. Ammonium nitrate decomposes relatively safely at 308 degrees Celsius when it's pure, but when it's contaminated with just 1% sodium chloride, the decomposition temperature drops violently to 239 degrees. Similarly, zinc oxide can trigger the decomposition of solvents like DMSO. Identifying and rigorously excluding these catalytic agents is a critical part of pre-plant thermal stability testing.
We've established the hazard potential and the need for precision measurement. Now we move to control. Chapter 6 focuses on reactor stability, revisiting the Semenov criterion to define the region where thermal runaway becomes possible, the parametric sensitivity region.
Right, the stability diagrams in Figure 6.2 plot the system stability. If the system parameters place the process in the low reactivity region, you just lose production because the reaction never ignites. But if the parameters push the system into that parametric sensitivity region, the cooling rate is just marginally sufficient.
So the system is on a knife's edge.
It is. It's highly susceptible to small, unavoidable external changes, like a pressure fluctuation in the cooling lines or a minor deviation in feed concentration. Engineers must design the process parameters to sit far outside this zone, ensuring the cooling margin is robust.
What's fascinating here is that the source material briefly references advanced, high-end methods like chaos theory and Lyapunov exponents. Why would engineers need to resort to such complex mathematics for chemical reactors?
This takes systems thinking beyond simple linear balances. Advanced methods like Lyapunov exponents are used to mathematically quantify the system's sensitivity to its initial conditions. For complex nonlinear reaction systems, the MTSR or TD249 might not tell the whole story.
So what does the Lyapunov exponent tell you?
If the Lyapunov exponent is positive, it signals chaotic behavior, meaning minute changes in initial concentration or temperature lead to wildly different, unpredictable outcomes downstream. This sophisticated analysis provides predictive power, helping process designers ensure the operating conditions are far removed from this region of extreme sensitivity where traditional engineering models might fail.
Let's pivot to the most common type of reactor in specialty chemical production, the batch reactor.
Right. The batch reactor, often a large stirred tank or an autoclave, is a closed system. All the reactants are charged initially, and there's no flow in or out during the reaction time. This presents a unique safety challenge.
How so?
Since the concentration is set at the start, the only practical way to control the rate of heat generation is by controlling the temperature via the external heat exchange system. Therefore, the entire safety margin of a batch reactor is highly reliant on the integrity of that heat removal system.
But the move from lab to plant in batch processes is often where systematic failure occurs, as illustrated by that devastating 1998 scale-up from semi-batch to full batch case history.
This incident involved the condensation of an amanamine with O-nitrochlorobenzene. The initial lab process was a much safer semi-batch process, where one reactant is added slowly over time.
Which controls the heat release rate.
Exactly. It controls the heat release and maintains a low concentration of unreacted starting material. But the plant decided to optimize by switching to a full batch system.
Which was a catastrophic decision without reanalysis.
It was. In the full batch, all reactants are mixed together before heating begins. This drastically increases the initial concentration and therefore the total energy accumulation potential, placing the system on a thermal cliff edge.
And this incident led to 9 severe injuries.
It did, because the reaction was initiated at 38 C but proceeds rapidly from 75 C, leaving a dangerously small margin. The product, a nitro compound, decomposed violently from 190 C, a crucial thermal threshold that was ignored. And critically, no specific hazard analysis was performed for the process change.
They just assumed the chemistry was the same.
They did, and the massive heat release from the accumulated reactants overwhelmed the system, and the safety relief system was woefully undersized.
The ultimate lesson, driven by the source text, is that thermal hazards must be systematically reevaluated whenever any process change occurs.
Absolutely. Scale up, batch size increase, or especially a change in the charging mode. The primary design strategy is achieving isothermal reactions, maintaining a constant, safe temperature, because temperature is the primary control knob.
But as we saw earlier at industrial scale, that's virtually impossible for highly energetic reactions.
It is. The focus has to shift to mitigating the consequences of unavoidable temperature rise. And the detailed analysis in Working Example 7.1 shows how quickly even a simple substitution reaction can escape control.
Right, it was designed to operate safely at 40 degrees Celsius.
It was, but if cooling failed, the calculated MTSR immediately shot up to 216 C. And the critical finding was comparing that to the decomposition stability limit. The TD24 is only 113 C.
So if cooling failed, the synthesis reaction would run away, and by the time it reached 113 degrees, they would only have 24 hours until the highly energetic secondary decomposition took over. At 216 degrees, that time margin would be cut to minutes.
Exactly. This confirmed that the cooling system was not just for production quality, it was a mandatory safety barrier against the decomposition trigger. This scenario automatically mandates strong safety measures, like a rapid quench system or high-capacity dump procedure, to immediately halt the synthesis before it reaches the decomposition temperature.
We've completed a pretty comprehensive tour of thermal safety, moving from general risk perception to the deep engineering calculations used to contain massive energy potentials, often measured in Mach numbers.
The primary takeaway has to be the necessity of the systematic process. Thermal risk assessment relies entirely on hazard identification tools like HAZOP and FTA, coupled with quantitative metrics like total heat release and adiabatic temperature rise, which define severity and determine the system's criticality class.
And the second, recurrent theme, driven home by the sulfonation, the DMSO storage, and the diazotization case histories, is that the danger is almost never found in the controlled main reaction. It is almost always found in the highly energetic secondary decomposition reactions,
which are triggered by accumulation, concentration effects, catalytic impurities, or simple cooling failure.
We also saw that the physics of scale-up is just unforgiving. Heat exchange efficiency drops drastically as reactor size increases,
Mhm.
and lab data that doesn't account for thermal inertia is inherently dangerous because it leads to a fundamental underestimation of the thermal potential.
Process safety is the ongoing discipline of acknowledging that heat production accelerates exponentially with temperature, while heat removal increases only linearly.
You now have the framework used by safety professionals, the architects of preventing catastrophe, to transition from simple chemical data to complex system design, ensuring stability across every possible process deviation.
And our source material mentions the concept of residual risk, specifically the unidentified risk. This is the hazard that the engineers simply failed to anticipate, often related to subtle changes in material purity or kinetic mechanisms that were not modeled.
So given the complexity we've demonstrated, the sudden catalytic effects of trace impurities like 1% salt, the highly nonlinear dynamics of temperature rise, and the need for high-end tools like VSP2 and Lyapunov exponents, the question remains for the industry.
How far can sophisticated calorimetry, meticulous hazard analysis, and comprehensive kinetic modeling push back the boundaries of that unidentified risk? Is it ever truly possible to eliminate the unknown thermal hazards solely through measurement? Or does safe chemical engineering ultimately rely on designing inherently safer processes, choosing chemistry and solvents that simply do not possess those volatile high-energy functional groups, regardless of how stable we model them to be at 40 degrees Celsius? That is the ongoing fundamental challenge for every chemical process safety expert.